And in this part of the video, let's talk about generalizing this idea of a parametrization of this conic section. So here's the key ingredient. First, we need to have 1 point that it's on this line, on this conic section. And we use the fact that degree is 2, so 1 point in here, and if you draw a line, the other points will intersect that circle, and that point has to be rational, together with the existence in here. So we can create this inverse map going from you're given in any slope, we can find the point that gives you that slope on that circle. Now the circle is conic section. So here's the bad news. It turns out this fact is from the theory of algebraic geometry. If Z represents a set of all rational solution in here, all rational solution, they're all in Cartesian product of rational numbers, and if there is a parametrization, rational functions that go from to Q to Z, whether it's a slope or whatever that things you come up with, the existence will contradict some genus formula. So this genus is some important topological invariant. Topological invariant to the complex solution of this cubic curve, and in particular this one has a positive genus, called the G is greater than 0. It turns out if there is a parametrization from Q to the solution set, and it's going to contradict some genus formula, so there will not be any parametrization, and this is proved using algebraic geometry theory. So here's one idea, that we required one rational point even in the conic section. So why don't we start with the same condition? Suppose we have one rational point. It's lucky we found one rational point, just like 1, 0 in here, something like that. Rather than thinking about all the line that sweeps across that circles, over here is a cubic curve, we're just actually going to draw a tangent line at that point right there. And then it's going to consume intersection degree 2. Meaning that if you try to find intersection points of this line that we're drawing in there, together with the cubic curve, and you will find a multiple solution, multiple zeros of that one coordinates there. So that's one interpretation of this intersection degree 2. So if you draw a tangent line, it's going to have at least 2 intersection degree. So this whole thing is a degree 3 we're looking at, and this consumed degree 2 already, so that forces remaining intersection point to be rational, because all this thing is happening in rational. So it's unclear what about the tangent line. How do we know that tangent line has rational coefficients? But it turns out it is. It is simple derivative formula applied to these formula in here, which are all rational coefficients. So the same phenomenon happens. We now have a degree 2. If you sweep this across the line, we have only one rational point. Seems like it's a degree 2, so we can't guarantee that the other two rational points have the other two intersection points have rational coordinates. But if you draw a tangent line, which consumes degree 2, then remaining intersection must be only 1. So these two, all with the rational coefficient, forces remaining intersection point in rational coordinates. So let me explain this phenomenon with this example. I changed the example from there to there because this obvious point we have, it's not going to give you it's not going to generate lots of other points in here. That was kind of unlucky accident. So I chose a different example, x cubed plus 2y cubed equals 3. And from there I think we see obvious point, that's not how I created this point. If I stick in 1 and 1, it's easy to verify that 1, 1 is a solution to this cubic equation. So this is a computer-generated image of this curve and this is where 0 is. This is coordinate 1 and 2 is very small, difficult to see, so that's how it goes. Put them down there. 1 comma 1 is roughly about here. That's the point there. So the idea is we're going to draw a tangent line, or something like this. Let's draw a tangent line. This is 1 comma 1, and we have this degree 2 intersection in here, and you can see it's going to go and eventually cross. That algebraically is quite simple. It's degree 3 must cross the other one if we have 2 intersection in here, multiple intersection. So that's the idea. So let's review how we compute the tangent line. This is usually introduced in the calculus courses. So this is not given an explicit function form. It's not solved for y. We have to use implicit differentiation, or if you know partial derivative technique, and that's even quicker. So you take this function, we usually call this capital F of xy, which is given by this entire thing, set to 0, like this. This two variable function, if you set this one equal to 0, that's equivalent to that. So what you're seeing here, how you compute the tangent line at a point a comma b. So if you plug in a comma b, such as 1 comma 1 here, that's going to be 0. That a comma b we choose. Tangent line is simply the partial derivative of this one with respect to x that goes in front of x minus a part, and this is a partial derivative with respect to y that goes in front of y minus b. So they're denoted like this with a partial symbol, and they're evaluated at a, b, and a comma b. And because this one does not have y part in it, it only has a, b in it. But in general, it's a mixture of a and b and mixture of a and b. So this is also the leading part of the Taylor series of the two variable function, but this is a fastest way to get the tangent line of a two variable function like this. So if you actually plug in 1 comma 1 in here, and you get 3 and 6 and x minus 1 and y minus 1, this is a tangent line, and we have this cubic curve. So we're about to solve this thing to set these two things equal to each other, or substitute y equals something to figure out what the other intersection point is. But in the process of solving this equation, remember the x equals 1 or y equals 1 is always a solution, and actually multiple solution. And like we did for the conic section, if you make the proper substitution, the solving an equation part is a lot easier. So x minus 1 is substituted with a z, y minus 1 is substituted with a w, then this point corresponds to the value z equals 0 or factor z, and the value w equals 0 or factor w when you change this one into a one variable polynomial. It's going to be degree 3 one variable polynomial, and there's multiple solution of a z squared and w squared in there in the process. So here's a calculation part. I wrote it down. This whole thing becomes now z and w. This is simply 1 and 2 if you cancel the common factor. And this x is replaced with a z plus 1. And here y is replaced with a w plus 1. And that's a cubic equation. And you can see the simple substitution law. You can write z equals negative 2w, right? If you solve this one for z, and you can substitute in here. Instead of, you expand all that, replace the z with a negative 2w, and expand all that. And you will see there's this w squared showed up, and that's correspond to this multiple solution in there. And it says the remaining point, the other point is supposed to intersect here, correspond to the value w equals 3, as I wrote it here. So if you go back to substitution rule and use this linear equation to solve for the other variable, in this case is x, it turns out y equals 4 and x equals negative 5. So if you go back over here, negative 5 comma 4, that you can verify that if you plug it in here, negative 5 comma 4 is also a rational solution to that point. Well, I hope you agree that this is really interesting idea to drawing the correct line and still being able to pull out this rationality there. So here's next jump. Let me go back to where we were before. So we have at this point 1, 1. By drawing this tangent line, we could find one more point over there. And once you have a rational point, you can repeat this idea again. If we have one rational point out there, why don't I draw a tangent line there again and see if it intersects in the other part. And I don't think it is a tangent line is going back to this line itself here. Tangency will be degree 4, so it doesn't make sense. If you draw a tangent line, it's going to hit some other point than 1, 1. So here we're going to repeat the idea for the newly found point -5, 4. So you go back to the tangent line formula and plug in these values and get this tangent line in here, and it's the same cubic is written, and we rewrite this entire thing in terms of z and w. It's simpler and easier to see how the multiple zeros kick in. It's the same exact type of calculation. It gets very tedious, and you will easily see that z squared or w squared shows up as you factor out. They're just some ugly numbers, but it's a beautiful rational solution that shows up again. So if you go through all that, it reveals us a different type of a rational solution. And I looked at this denominator and looked at the prime factors to make the comparison of what happened with the conic sections. And when you go through the operation, you always have the same type of a denominator, but now we can see new prime factors showing up. So I collected together so far the 3 points from 1, 1. Draw the tangent line, we got this point. We draw the tangent line there, and we got this point. And of course you can keep repeating just drawing the tangent line, and it'll introduce us to more and more complicated looking solutions. And denominator will be more and more prime factors kick in. So I'm redrawn the curve in a bigger scale. So we started here and draw the tangent line and found the second point. We draw another tangent line and draw the third point, and you can go back and forth like that. That was the idea. Right, now we have 3 points, and here's a new idea. If we have these 2 rational points, not this one and that one, so 2 is a part of tangent line for this line and that line. If you look at this 1 and 3, they're not part of the same tangent line. So if you look at these 2 points, and the 2 rational points we have here come from different tangent line. If you draw the secant line in here, for example like that, we have 2 rational points in degree 1 and intersecting the degree 3. So degree 2, that's a 2 rational point, subtracted from entire degree 3, you know it's degree 1 that forces its rational points. So whatever that point we're observing right there, that must have rational coordinates. So I use the same tangent line formula for these 2 points. Actually, not the same. It's different. It's not tangent line. So we have 2 points, and you can write down using Points law formula of equation of this line, and that's what I wrote it here. Okay. We have this nasty coordinates for the third point that leads us to, and this 2 coefficient for the line, and here's the same cubic, and make the substitution and go back and change this equation in one variable in z and w, and this time there's no multiple solution, but we know the w value that is associated with that, which is namely y coordinate plus 1, and w value associated with that. And from this point we know those values. So when we go to a degree 3 equation, we know 2 of the solution already, which is coming from in here. So here's the equation that all things replaced in terms of z and w, and this equation is written in terms of z and w, and we substitute back what z is in terms of w, and then leads us to this degree 3 equation in W. So you can see this constant term is missing. So W equals 0, that corresponds to this part in here. This is where W value is 0 because Y is 1, so Y minus 1 is a W. So you can factor out W, and you can also calculate the W value in here, and that reveals us one of the rational solutions of this complicated looking equation. So here's what I was saying. W equals 0 is one of the solutions. If you look at the W value of that, Y coordinate minus 1, and that's W value. So we know this appeared as a factor of these cubic polynomial. So how do we figure out the remaining linear factor? Long division is one thing. You can cancel that W and actually dealing with a slightly lower degree polynomial, but doesn't really change the amount of calculation. But here it is. If you do the long division, it'll give you remainder 0 and the quotient. Now it turns out that this degree 3 polynomial factors like this is known factor already from 2 previous points, and the third linear factor looks like this complicated. So if you go back to this substitution, we have this giant rational solution that is in between that 2 points right there, right here, right? And their coordinates are roughly 1.44 and 0.18. But now we have two methods introduced so far. One is drawing the tangent line, and the next one is drawing the secant line if you have 2 rational points, and the third one will be also rational. So if you think about these two methods, it's just like if I have 2 points, or if I have 1 point, from there, kind of we can generate a third point. It looks like binary operation. So you can define that as a binary operation, that is extended the earlier binary operations. But when we say binary operation, often we kind of expect that associativity and some of the operators sound naturally satisfied. It turns out in this construction of a binary operation is not quite satisfying associativity property, but there's a little tweak that it can be done to that, such that this turns to a binary operation. So rather than defining, if I have 2 points like this, and defining it to the third point, they realize that if you do a slightly different way, the third point we operate one more time, and you define this one as a 0 points. This point 0 points here, unfortunately, is not on this plane in here. It has to be some imaginary auxiliary point you have to throw in so that this operation makes sense. But arithmetically and or geometrically, it's a lot more complicated than the conic section operation we have introduced. And throughout the many results and fascinating results in elliptic curves, it proves that, or geometrically, it proves that arithmetic is coming out of this operation is a lot more complicated, and more importantly, it's a lot more interesting, and it has huge application to number theory. Let me end this part of the video, or this entire series of the video, and here introducing this theorem called Mordell theorem, or generalized version. It's called Mordell-Weil theorem for higher and higher curves, high degree curve. And I used this finite field example before. All for conics before that finite field case, there's a single generator that if you do the operation to itself, it reaches everything. And I show that by looking at the same conic over the rational numbers, there is no finitely many generator. And if you do the operation, you will reach every solution. It's quite extreme. But another interesting thing that happens in elliptic curve, that is an indication that is very different phenomenon from just playing with the numbers. That's how we observed it in here, that there are actually finite subset of solutions that if you do this operation over and over, playing with the tangent line and playing with the secant line over and over again, and it turns out it reaches all the solution inside that cubic solution. cubic curve. So this is called Mordell-Weil theorem. And natural thing is that, oh, if there's a finiteness, and what is the minimal number to of the generators to generate all the solutions. There's been huge progress made to actually algorithmically calculating the number of minimum solutions, but it's still that algorithm, whether being deterministic or not, is still an open problem, and that's or constructing elliptic curve with this type of curve with a large minimal generator, minimal set of generator, and things like that. There are many interesting questions and conjecture related to this curve of degree that's just one higher than curve of Koenig's is well understood, and this is already very complicated, although it's just bumping up degree just by one. Therefore, it's a natural object to study, but it turns out all the higher arithmetic can be also understood or controlled nicely by this particular class of curve, of elliptic curve. And many number theories are focused on this particular equation. What I mean by this particular equation is that degree 3 in 2 variables. Thank you so much.